Most developers use async.io every single day without really knowing what the event loop actually does. Today, we are going to fix that. When you write async code, you're not just writing logic, you're really writing instructions for a scheduler. If you don't understand that scheduler, you're flying blind. Without that fundamental knowledge, you'll eventually hit race conditions, blocking calls, and mysterious slowdowns, and you won't have the tools to figure out why. Python gives you three primary concurrency tools. First, threads. They share memory and run in parallel, making them great for I/O-bound work with shared data. Then we have processes. These run on separate CPU cores, providing true parallelism. This is the right choice for heavy, CPU-intensive mathematical work. Finally, there's async. It uses a single thread, no parallelism at all. What it gives you instead is cooperative multitasking, managing thousands of tasks with almost zero overhead. So, what is the event loop really? At its core, it's just a loop, but it's a loop with a very specific job and two very important lists. Here's the model. The loop manages a ready queue and a waiting list. On every single tick, it picks the next coroutine from the ready queue and executes it. That coroutine runs until it hits an await keyword. If the thing it's waiting for isn't done yet, like a network call or a file read, it stops right there. The loop then moves that coroutine into the waiting list. It's no longer using any CPU time. It's just parked there, waiting for its I/O operation to resolve. Once that external event resolves, the coroutine moves back to the ready queue. The loop picks it up again on the next tick and resumes exactly where it left off. That's it. When you call asyncio.run and pass in your main coroutine, Python creates a brand new event loop, wraps your coroutine in a task, and puts it in that ready queue. The loop starts ticking immediately. Your coroutine runs line by line until it hits an await. This is the moment where you yield control back to the scheduler. Say you await asyncio.sleep for 1 second. Your coroutine suspends and moves to the waiting list. It doesn't block the program, it just steps aside. Exactly 1 second later, the timer fires, the coroutine moves back to ready, and the loop resumes it. This is how you manage thousands of tasks concurrently. Let's look at exercise 1 from the repo. We have a say after coroutine that waits for a specific delay and then prints a message to the console. In ex1_main, we call it twice in sequence. First for 1 second, then for 2. Because we use await directly, the loop finishes the first call before even starting the second. The total execution time is exactly 3 seconds. This is sequential, one thing after another. The loop is basically idling while each task waits its turn. Now look at ex2main. Here we wrap the calls in create task before we await them. This tells the loop, go ahead and schedule both of these right now. The loop interleaves them. Total time drops to just 2 seconds, the duration of the longer task. The loop didn't change, you just changed how you scheduled the work. One very important warning. Async is not for CPU-bound work. If you're running a heavy machine learning model or compressing huge images, await won't save you. The loop can't switch tasks if your coroutine never yields control. If you're doing heavy number crunching, use processes instead of async to keep things moving. Also, be careful with blocking library calls. If a library isn't async native, it will block the entire loop. Always verify support before you reach for a library. The big takeaway: the event loop is a cooperative scheduler. You yield control with await, and it runs whatever else is ready. It's a team effort. The whole system depends on every coroutine playing nice and not blocking the loop. Next up, we'll dive into coroutines and tasks, the actual primitives you schedule.